Okay, so now let me talk about Riemannian quotient manifolds. So now let's say we have a quotient manifold M, which is the quotient of another abstract manifold M bar by some equivalence relationship tilde, okay, where the structure space M bar, right, is endowed with a Riemannian metric. Let's call that G bar. Okay. All right. So again, you have sort of this kind of picture here, right, where you have M bar, and then this base space here is M. You have a projection from M bar to M, which maps points in M bar to the corresponding equivalence classes. Okay, and you have a metric on the original space. So you want to ask whether or not you can, given a metric on M bar, it's like induce something on M. Okay, and so I should say early on that, you know, in general, it's like you can't do that on an arbitrary metric. It's like G bar and M bar. G bar has to have certain nice invariance properties for it to define or to induce a well-defined metric. It's like on M, which is the quotient space. Okay, so let's see how you go about doing this. So if when we were discussing embedded submanifolds and talking about how a metric, it's like on the Riemannian metric on the embedding space induces something on the embedded submanifold, we had sort of talked about, you know, it's like trying to take vectors, it's like on the space you're working with, and then inducing a vector, it's like on the space M bar where the Riemannian metric is given to you, and then applying it. Okay, so let's try to do something similar. If you recall, with quotient manifolds, there isn't a unique lift, if you will, from a vector, it's like on M, it's like to a vector on M bar. Okay, and in order to achieve uniqueness, we needed to introduce this idea of a horizontal distribution, right? So to define a unique lift from sort of Tm to Tm bar, right, we needed to introduce a horizontal distribution which sort of assigns to each point x bar in M bar, right, a sort of subspace of the tangent space at x bar to M bar that is complementary to the vertical space. The vertical space is induced by the projection. So if you recall, it's like the way you do it is that if you have a point x on the base manifold, you look at the pre-image of this, you look at pi inverse of x. This gives you something now which is in M bar, and you can look at the tangent space to that. So it's complementary to Tx bar, okay, of pi inverse x, right? Okay, or if you prefer, it's like, let me write this as pi inverse pi of x bar. Okay, so this is the vertical space, and what we mean by complementary is that you can write the tangent space to the full manifold M bar at the point x bar as the direct sum of this space and that horizontal subspace. So I would say horizontal So how do you do this? Okay, so of course it's like there's some arbitrary choice here, but if it turns out that you've already endowed m bar with a Riemannian metric g bar, then there's a very natural choice of a horizontal subspace which is complementary to this vertical space. And that natural choice is obviously the orthogonal complement of that vertical space with respect to the Riemannian metric g bar. Okay, so since m bar is endowed with a Riemannian metric, g bar, right, there's a natural choice of horizontal space, right? So I'll have the horizontal space at x, right, to be just equal to the vertical space at x perp. Okay, so this is the set of vectors, okay, in the tangent space at x bar of m bar, right, with the property that the metric applied to these vectors equals to 0 for all vectors, all test vectors, if you will, which are in the vertical space. Okay. All right. So why do we do this, of course? And the reason why you do this is that once you've defined this notion of a horizontal distribution, then there's a unique lift from a vector. It's like on M, it's like to a vector in M bar, which has a property that that vector in M bar projects to the vector in M, plus it's in the horizontal space. Okay, so this is of course what is called the horizontal lift of a vector in M to a vector on M bar. And again, the point is that there's uniqueness in this construction now. Okay, so given sort of the horizontal distribution, right, there is a unique horizontal lift of some vector cx in txm to cx bar, right, which is in tx bar m bar. Okay, so it's horizontal lift, if you will. Okay. All right, so so now you're in business. It's like because you know you want to define a metric. It's like on M, right? In order to define a metric on M, you need to see how it acts. It's like on two vectors in M, and given those two vectors in M, it's like we use the horizontal lift to lift them up to two vectors in M bar, and we apply the Riemannian metric, which is given to you, G bar, to those things, and we check. I mean, we use that then as a candidate definition for the induced metric. It's like on M. Okay. So that's the plan here. Okay, so let me just keep the picture there. Okay. So given x on M and Cx and some two vectors, it's like in Txm, right? And x bar in M bar such that the projection of x bar is x, right? You can consider G bar, X bar, right? where these things are the horizontal lifts. Are the horizontal lifts of the original vectors which are given. Okay, so you can consider this, right? And the point is that this thing, in principle, depends on x bar. Okay, so in general, right, this thing depends on x bar. Okay, and so what needs to happen basically is that if it turns out that this expression is the same for every x bar which projects to x, right? So if star is the same for every x bar such that x bar, well, the projection of x bar is equal to x, right? Then we say that, you know, it's like this metric g bar, it's like on m bar, has some nice invariance property which is compatible with the notion of equivalence, which is induced by the equivalence relationship, and then it induces a well-defined metric on M. Okay. But that's something which imposes. I mean, that's something which is not always true. It's like it depends on sort of, you know, G bar. It's like behaving nicely, if you will, with respect to the projection, right? So then it doesn't depend on the choice of representative, if you will. And this induces okay, so then if it doesn't depend on x bar and this, then okay, so let me just say it this way. So if it doesn't depend on x, then this induces a Riemannian metric G on M, given by, as you might expect, G of these G applied to these two vectors, right, is defined to be G bar evaluated at the lift of the point and the horizontal lifts of the corresponding vectors. Right, so this is not always, the point is that I should say that this is again not always well defined, right? It requires that G bar has a certain nice property that this actually gives you a well defined thing. So if it's well defined, then obviously it induces a metric on this quotient space, but it's not always the case that this is well defined. Okay. All right, so if you endow M, which is this quotient manifold, by okay, with this metric, makes with this Riemannian metric, right? Makes M a Riemannian quotient manifold. Of M bar. Okay. All right. So again, it's like, you know, in general, it's a quotient manifold. It's like, but if you want it to be a Riemannian quotient manifold, then the Riemannian structure on M has to be induced by the quotient operation. It's like from the Riemannian structure on M bar. Okay. And then the other remark is that this canonical projection gives you a Riemannian submersion. Okay, so also so the natural projection pi, which is a map from m bar to m, right, is a Riemannian submersion. Okay, so so you can then ask, it's like in this setting, it's like what happens to the things which we defined. It's like using the Riemannian metric, in particular the gradient. Okay, so so let's say that if f bar, right, is a function on m bar with the property that it is constant on equivalence classes, which is to say that for everything which projects to something, to a given thing, it's like on M, it's like, you know, f bar evaluated on that set of points, this all gives you the same value. If that's the case, right, so if it's constant on equivalence classes, then it induces a function f on M, right? Then it induces a well-defined function f on M. Okay, so so you can ask how the gradients, it's like, of these two functions are related to each other. Okay, if you are in the case of a Riemannian quotient manifold. Okay, so so if you take grad f bar at x bar, okay, then this is equal to grad of f bar at x bar. Okay, so so let me make the following observation. So you note that grad f bar x bar belongs to the horizontal space. And you know this because, you know, in order for it to induce a well-defined function, it's constant on each equivalence class. Okay. Okay, so let me sort of develop the argument. Okay, so since f bar is constant in each equivalence class, right, it follows that g bar x bar of grad f bar x bar in some vector is just the d of f bar x bar in this direction, which is equal to 0 for all vertical vectors. See, because vertical vectors come from curves, it's like which are in the same equivalence class, right? Okay, and you can write this, it's like in terms of the composition of f bar, it's like with the curve, if you will, associated with this vertical vector, which again, it's like is a curve which takes values in the same equivalence class. Okay, so this implies that so hence grad f bar x bar is orthogonal to the vertical space, which means it's in the horizontal space, right? So that's how you show that grad f bar x bar is in the horizontal space, is that it's orthogonal to the vertical space. Okay, and then you can write this. There's some notation then for the projections onto the horizontal and vertical spaces, which I'll just write down here. Okay, so we use the notation P x bar h, C x bar, and P x bar v, C x bar, right, for the projection of a vector C x bar in the tangent space at x bar to m bar, right, onto the horizontal spaces and vertical spaces. Okay. All right. So that sort of concludes the discussion about again how if you have a Riemannian sort of metric structure on the sort of the structure space, and it has some sort of invariance property that it induces a Riemannian structure on the quotient manifold. Okay, so let me just stop here for now.